Welcome to the Maxim Integrated Webinar Series. Today, we're going to learn how to cut development time and minimize solution size with out-of-the-box USB Type-C solutions. I'm Ben Smith, and I work in Maxim's Training and Technical Services Group as a principal member of the technical staff. Our presenter today is Sagar Kure, and Sagar is a business manager with Maxim's Mobile Power Battery Management Group. He holds a Master of Science in Electrical Engineering from Stony Brook University and a Master of Business Administration from Arizona State University. Okay, Sagar, take it away.
Thanks, Ben, for the kind introduction. Welcome, everyone, to this webinar to cut development time and minimize solution size with out-of-the-box USB Type-C solutions. It's no secret that USB Type-C has really gained in popularity over the last few years, and it's expected to stay that way for a number of years to come. At the end of today's webinar, I'm hoping to leave you with a number of solutions that will accelerate your design and eliminate the learning curve that you might otherwise face. So let's jump right into it. So here's today's agenda. So we'll start off by first looking at why you should care about USB-C and what really is new in that particular standard. Then we'll jump into a little more detail about what the architecture looks for USB Type-C charging. Then, obviously, you may have different types of applications. So depending on the power level and the type of application, you may have different needs. So we'll look at a few options on how, first of all, you would choose the right solution for your application. And then we'll go into a little more detail about each of the types of categories of solutions, starting with up to 15 watts of charging power. That's for standard USB Type-C. And then we move on to power delivery, which is more than 15 watts of power. Then finally, we'll look at some of the design resources that we have on offer. And then we'll end with a number of question and answers from the audience. So what really kicked off the USB Type-C in the market? So just looking at the market segments where USB is used, USB Type-C is used, it all really started with smartphones. Smartphones were early adopters of the Type-C standard, and it really proliferated across a broad range of markets. Typically, smartphones use smaller chargers, at least historically, 15 up to maybe 27 watts of charging capability. And these devices used very, very highly integrated solutions with custom PMICs and a lot of functions built into the same IC. On the upper end of the spectrum, we also had laptops and Chromebooks that have a much higher power level, so about 45 to 100 watts. They also use USB Type-C, and these power levels are so high, so big, that typically you will find chargers with external FETs, not highly integrated. So that is really the predominant market, at least until now. But as the Type-C standard became more popular, we started seeing a lot of proliferation in many, many different applications that are shown here in the middle. So from DSLR cameras to point-of-sale devices, radios, gaming devices, everything these days seem to have USB Type-C. Now, what's unique about this segment is that it's small enough that it may need a smaller, highly integrated charger that minimizes the solution size. But it also likes the advantage of USB Type-C because the power levels are not low enough that you can use the legacy standard anymore. And plus, the USB Type-C with its convenience of the reversible plug is an ideal solution for this segment. And this is the reason why we see the fastest growth for USB Type-C in this particular segment. So just to take a step back, it's probably important to understand what is new with USB Type-C. So on the left, I have an image of a legacy cable, which is a Type A to Micro B type cable. And What you'll notice, obviously, is the connectors are different on both ends of the cable. They are non-reversible. I mean, how many times have we tried to plug it in to a port and you have to reverse the direction? In most cases, the standard only allows up to 7.5 watts of power capability. There were some proprietary standards that extended it beyond that, but when it comes to proprietary, it's no longer universal. So Type C tries to change all of that. First of all, the cable has the same connector on both sides, and that particular cable is reversible. So when you plug it in, you can be assured that it will go in the first time. And then as far as power levels are concerned, the Type C standard really extends that much higher. So with the standard Type C, you can get 5 volts up to 3 amps of current. That gives you 15 watts of power just by default. You can also extend that power by increasing the voltage. So you can negotiate voltage from 5 volts up to 20 volts and up to 5 amps of current. Mind you, the 5 amps of current requires a custom electronically marked cable, but it is possible to go up to 100 watts if you have all of these factors in place. So now that we know what is different with Type C, let's look at the typical Type C charging architecture. So this is a block diagram showing all the various blocks that are involved in a typical Type C architecture. Let's look at each one in detail. So the first one is the USB Type C, the CC detection block. So this block serves basically 3 purposes. Number one, it allows you to identify the orientation of the cable. Second, when the cable is connected, it allows you to allows the source to advertise its current capability. And finally, if you have a USB power delivery source, you can also negotiate the power depending on the capability of the source and voltage and current levels that the sync device is capable of accepting. Next, we have the BC 1.2 detection block. Now, BC 1.2 stands for battery charging 1.2 specification. This is a legacy standard from the USB 2.0 specification, and it was primarily used for charging devices up to 7.5 watts. Why do you need the legacy standard on a USB Type-C architecture? So the reason is this, we have a lot of legacy adapters, from older devices or just adapters that have been lying around in our house, or we just like to use them for travel or maybe one in the office and so on. So it is important to support the legacy standard because of the large installed base. And so with the Type-C architecture, the BC 1.2 detection block almost is a mandatory block. Then we have the charging device itself. This is where your power electronics reside. So you may have a converter that efficiently converts the power from the USB port to what the battery needs, both fast, efficient, and safe. So that is the power electronics block. And then finally, you also need traditionally a microcontroller, which allows you to coordinate the operation of all of these different blocks that are seen on this slide. So let's take a look at how the actual operation works. So consider first a USB Type-C source. In this case, you have a Type-C source connected to the other end of the cable, and the device needs to start negotiating or identifying what the power capability is. So this is where the MCU polls the CC detection block for the presence of a cable. Once that cable is plugged in, the source identifies what capability it can provide. The MCU then reads from the CC detection block what that current capability is. And based on that capability, it configures the charger and then enables charging. Next, if you have a USB power delivery source. So the initial section, the USB Type-C detection, it works the same as what we saw in the previous slide. But with power delivery, you also have a further step. In this case, there is a power delivery source which advertises the power capabilities, which includes the voltage as well as current levels. These power delivery capabilities are known as power delivery objects. So typically, the source is going to send a list of power delivery objects back to the CC pin detection block. The MCU then reads from the CC detection block and looks at what that list looks like. So you may have multiple capabilities. It may have 5 volts, 3 amps. It may have 15 volts and 2 amps and so on. It may have a number of these options. Now, based on the preference of your system, you may pick one of those power delivery objects to start operating and start charging. So when the MCU selects that particular object, it sends that signal back to the CC detection block, which in turn sends that confirmation to the power delivery source. Once that is established, the voltage source is enabled and the V bus goes high. And at that point, the MCU will enable and configure the charger and start charging. Then finally, if you have a legacy USB source with BC 1.2 detection. So in this case, the operation is somewhat similar. You do need the BC 1.2 detection block. And so the MCU polls the BC 1.2 detection block for the type of source that's detected. The cable is connected. The block identifies the source capability and the type port, and then sends that back to the MCU. And once that MCU receives that message, it then enables the charger and configures and enables the charger for charging. So there's a few things that are evident from all of these block diagrams. So number one, you can see that there are multiple blocks that are required on the system. What this means is you need to have very complex hardware with various blocks, and invariably it leads to a large solution size and also increases the cost. On the software end, you need to have the very precise firmware developed that coordinates the timing and operation of all of these different blocks. And then also control the charger and define how the system should behave based on the different sources. So this does require a lot of expertise and on the USB specification, which, let's face it, not everybody has that. And there's a learning curve associated with it. So that essentially results in a longer development, and it delays your time to market. So how do we avoid these situations, and how do you overcome these problems? Let's take a look at that. So as you know, there are a number of solutions available on the market, and I want to just spend some time guiding you to choose the best solution depending on the type of application that you have. So this is a matrix that shows all the different options available, and I've classified them essentially on 2 axes. One is in terms of the power level, and that's the vertical axis. And then the second consideration is how simple or how flexible your system needs to be. So traditionally, you've seen the block diagram for the architecture. What usually was defined before was that there would be an MCU-based design with an I2C bus going around all of the different blocks and coordinating the operation of each one. This is what the traditional USB Type-C architecture and more recently the USB power delivery architecture has been. So in this particular case, you may have 3 separate blocks. One is the power delivery controller. You may have a charging device, and you also have the MCU for coordinating all the different aspects of your design. Now, this is because of power delivery, the power is greater than 15 watts. So you're going to see applications such as a digital camera or a VR headset. On the lower end of the power, you may still have multiple blocks, which is an I2C based charger, but with an integrated USB Type-C detection. And in this case, you may still want to have some coordination with the MCU, although majority of the USB detection and charging function can be performed autonomously within that charging block. So in this case, you may have handheld computers or scanners and so on. But then as the standard becomes more and more popular, there is a need to go more hands-off sort of standalone operation, where your charging device and your the USB detection is completely independent from the rest of your system. This was not possible before, but we now have products on the market which allow you to do that with absolutely no firmware development at all. So what that includes is a completely integrated IC, which has standalone USB Type-C detection, in addition to the charger, and also with no firmware development, which can be configured all completely via resistors. And as the standard becomes more and more popular, there is also the push to have the power delivery standard, which is also standalone now. So in this case, we have products which I'll go through in more detail later, but we have products which have standalone operation with a USB power delivery controller, which performs all of the negotiation and control for you. And you also have a charging block which performs wide input voltage range and high efficiency and very high performance charging. And in this case, you may have applications such as two-way radios or set-top boxes and so on. So there's another consideration to look at. So what is the topology of your system? So if you look at the cell count, if you have just a single cell battery, in most cases, you're going to be fine with a simple buck converter, a buck charger. And the reason for that is a typical lithium-ion battery is always going to have a voltage which is less than 5 volts. And the USB power delivery standard goes from 5 to 20 volts, or if you use the standard USB Type-C, you're going to be operating at 5 volts input. So whether you have less than 15 watts or more than 15 watts with power delivery, a buck converter is going to be sufficient for this particular single cell battery application. Next, if you have a 2 or 3 cell application, but in some cases, you may still have power levels which are less than 15 watts. So if the power level does not require USB power delivery, you're going to have a 15 volt input, a 15 watt maximum power, but a 5 volt input. And in that case, you need to boost your voltage up to the battery level, which may be 8 volts or 11, 12 volts, depending on whether it's a 2 or 3 cell battery. So with a 5 volt input and 8 to 13 volt output, you can always use a boost converter with integrated USB detection. Then finally, if you have a 2 or 3 cell system, which requires more than 15 watts, now this is where you need USB power delivery. Now with power delivery, your input voltage can vary from 5 volts to 20 volts, but your output voltage has to be between 8 to 11, 12 volts approximately. So what this means is your output voltage can be either higher or lower than your source input source voltage. So because of that configuration, you do need to have a buck boost converter. So it would need to be a buck boost charger with a wide voltage range that operates from 5 volts to 20 volts. So that would be the consideration for more than 15 watts of power and a 2 or 3 cell battery. Okay, so with the Type-C or Type-C power delivery considerations, you have 2 separate types of options. So number one, with lower power levels, it's possible to have all of the solutions or all of the blocks in the architecture integrated into a single IC. The advantage of this is that you have everything integrated into the same IC. It coordinates all of the operation between the USB port and the charging function. And essentially, it can be configured either with I2C or with just resistor configuration. And it can operate pretty much autonomously from the rest of your system. If you have a higher power system, you do need to have a power delivery controller. And because of the higher power, typically you're going to find this in two separate chips. So one chip for the power delivery control and one for the charger. Now, in this case, what you need to look for is out-of-the-box compliance to the standard. With the PD 3.0 is the latest standard for USB power delivery. And then for the charger, you need to have a wide input voltage range. So it can operate from 5 volts to up to 20 volts. And of course, because of the high power, you do need to have high efficiency to minimize the solution size and heat dissipation. Now, in this case, the solutions that are available can be controlled with an MCU, or they can be standalone from the PD controller by itself. Okay, so now let's look at some of the solutions available for low power, which is less than or equal to 15 watts of charging. That uses just the Type-C standard by itself. So the simplest solution that is available today is the Maxim 77751, which is a 3-amp buck charger, which is completely standalone. So it integrates USB Type-C and DC 1.2 detection on the same chip. It sets the input current limit automatically after detecting the type of USB source. And it integrates the power source and the battery charging state machine to efficiently and safely charge the battery. And it operates even with a dead battery condition. It also offers the reverse on-the-go operation up to 5 volts and 1.5 amps in case you want to power an accessory device. And it's all configured with resistors or with a GPIO signal. So the unique thing about the Maxim 77751 is that it does not have any I2C communication or any firmware development. So it simply requires just 2 resistors and maybe an I/O port that will enable or disable the charger. So it's the simplest solution with fully integrated USB Type-C detection. So this image really illustrates what is the advantage of having a very, very highly integrated solution. So on the left, we have a picture of a typical charger, which it's very common to see the BC 1.2 detection block integrated in the charger. But often for USB Type-C, you're going to need an external IC that effectively performs the CC pin detection. Now, what is available on the market is it includes multiple blocks and a lot of components on the board. Whereas with the Maxim 77751, with the high integration, you're able to minimize the solution size. In this case, it can be as much as 33% smaller. So with the Max 77860, this is a I2C based charger, which integrates USB Type-C and offers a lot of flexibility in addition to the integration of the USB detection. So it also has an always-on LDO, and this will be used primarily where you need a little more flexibility from your system. So for example, you may have a system which requires maybe one battery termination voltage under certain conditions, but as the system ages, you may want to reduce the voltage, termination voltage for the battery. So with the I2C functionality, you have full functionality, full configurability over the lifetime of the product. And again, even though we have that flexibility, it still operates fairly independent. So once you configure it in the beginning, it will operate without any MCU intervention beyond that. And then if you have 2-cell batteries, then we also have a boost charger, which is the Max 14748. Now this one is also, it operates at 5-volt input. For standard USB Type-C up to 15 watts. And it also includes a D plus and D minus switch. So for example, if you have a system where you need to perform the USB detection initially, but then after that detection is complete, you want to use the data lines for USB communication, then you can always switch them to your other device and have that communication performed separately after the charging detection is complete. Again, this can be configured in the beginning and it operates without any intervention afterwards. So those were all solutions that are available for up to 15 watts operation. Now let's take a look at the options for USB power delivery, which is more than 15 watts of power. So as I showed before, the power delivery solution generally involves 2 chips, USB power delivery controller, and another chip, which is a wide input voltage, either a buck boost or a buck charger. So with the power delivery controller, we have the Max 77958, which is out-of-the-box compliant to the latest USB power delivery standard, which is PD 3.0. It offers a very high input voltage absolute maximum rating. So it also provides a lot of protection, including shorting protection on the CC lines, as well as other advanced features such as moisture detection. It also offers the legacy detection for BC 1.2 detection, and also a D plus D minus switch. And it can be configured to operate either autonomously or with an MCU. The charger that we have offered, either a buck or a buck boost charger, it has a wide input voltage range, integrated FETs to minimize the solution size, and very high performance. And we'll look at all of these in detail next. So with the Max 77958, this is a very unique product because it allows you to customize the behavior of your system and also be compliant to the USB power delivery standard. So you have built-in Type-C detection as well as BC 1.2 detection. So many of the products for power delivery that are on the market today, they do not contain the BC 1.2 detection. So this is the only product, the Max 77958, that does include it. It offers a number of advanced features, so including a dual roll port support, as well as fast roll swap. So if you want to switch from source to sink very quickly, this part will allow you to do that. It also supports programmable power supplies. It detects the cable orientation and a lot of additional features. I also mentioned some of the advanced features for protection, for robustness, which includes moisture detection. So a lot of our portable devices these days, we use them in all sorts of environments, and moisture detection is important because it may affect the safe operation of your device. So if you can detect that moisture detection with same IC, it allows you to give advanced warning to the user and maybe limit the usage to prevent any unsafe conditions. But in addition to being fully compliant, you also have the ability to customize the operation of your device. Because let's face it, every application is going to need a little bit of different type of behavior, depending on the type of conditions that you may encounter. And how is this achieved on this part? So we have non-volatile memory built into the IC, which allows you to configure the device to operate according to the needs of the application in your factory. So you can configure it in your factory during your final test and have that in the non-volatile memory for the lifetime of the product. And you can also update that non-volatile memory in the field if needed in the future. So speaking of the customizations, there are 2 basic configurations that you can operate in. So one on the left is the standalone type operation, where you don't necessarily have any additional microcontroller. So one of the unique features of the MAX 77958 that enables this operation is that it has a master I2C port. This master I2C port directly controls the companion device, which may be a charger or a DC to DC converter or any other type. What it allows you to do is to negotiate autonomously the power delivery voltage and current levels, and then configure the charger based on the type of power source that is connected. And all of this is performed because you can pre-configure your operation in the non-volatile memory of the MAX 77958. Well, in some situations, the standalone operation may not be sufficient, where you may have some limitations such as very simplistic operations. So in cases where you may need to have some complex looping operations. So if there's like a if-else kind of conditions that you need to act on, then it is recommended to have an MCU in the system. Now, in this case, the MCU really coordinates the entire operation. The MAX 77958 still performs the main USB detection and provides the status information that can be polled by the MCU. The 77958 can generate interrupts that allow the MCU to only poll when needed, instead of having a periodic function that just continuously reads from the MAX 77958. This allows the MCU to be offloaded from all of these complex actions that may happen on the Type-C port. And then once the MCU gets that, reads the information from the port, then it can configure the charger, or it can allow the MAX 77958 to configure the charger as well. So it provides the maximum flexibility and most independent operation that you may need for the system. So speaking of customization, let's go into a little more detail. So we have a graphical interface that allows you to program your customization script in the factory. So I just have some illustration on how this is performed on the graphical user interface. So we have a customization script generator, which is present in the EVKit software. And when you open that interface, you have an interface where you can type in the commands that you would like to act on. And so depending on the different types of events that occur on the USB port, it generates an event list that you can perform customizations on. And let's take a look at some of the examples for this. So this is just a very simplistic example, which of course, this does not quite capture the range of possibilities, but I just want to give you a flavor of it. So at the very fundamental level, your device is going to power on, right? And so when there's a power on reset detected, you may want to configure your system for your initial state, whether it's to enable the charger as a sync mode, or if you want to just maybe toggle an LED, you can perform all of those functions based on the power on reset event. Another event may be when you detect a cable connected and that your device has entered the sync mode. So in this particular case, you want to read what the power capability of the source is, and then configure your charger to operate at that particular power level. So this is another example. The third example is if we've seen the example of moisture detection. So if you sense the presence of moisture, it's going to generate an event which essentially tells you that there is moisture detected in your system. And in this particular case, all I'm doing is enabling a GPIO pin to maybe indicate on an LED or maybe to the microcontroller that there is a presence of moisture, and therefore you need to do something either to limit the operation or shut down the device, or whichever way you want to handle it. So this just gives you some examples on how the customization works. So finally, you can program this into your system using the graphical user interface as well. But then in the factory, you may have this programming done either through the USB port or through a test fixture. There's multiple options. gives you all the flexibility you need. So then looking at some of the charging solutions, so we have a couple of buck boost chargers. So this is the Max 77, 960 and 961, which is a wide input voltage range, 3 or 6 amps output charging capability, and 2 to 3 cell compatibility. Very high efficiency, 97%. It includes all of the power FETs that are required in this charging application. And it can be configured both through I2C or using an autonomous resistor-based interface. And then we also have a smaller version of this IC, that's the Max 77962, which is a 3.2 amp charger, which supports 2 cell batteries and is offered in a WLP package. And just to illustrate the size advantage when you look at the fully integrated solution, such as the Max 77962. So on the left is more of a traditional buck boost architecture, which is a buck boost controller with external FETs. With the Max 77962, you can shrink the solution size by up to half with all the FETs integrated and a very, very high performance small solution size. We also have the Max 77, 975 and 976, which is single cell buck charger for USB power delivery. These chargers operate up to 3.5 or 5.5 amps output charging capability, and they offer very high efficiency up to 90% or more, even at high input voltages, which is not very easily found in the market. We also have a very high discharge current capability. So it offers up to 10 amps of continuous discharge current, which is perfect for applications where you need very high performance or very large transient loads. This part can support that very easily. And to put all of these blocks together, we also have reference designs that are offered that include all of these different blocks, including the power delivery controller, the buck boost charger, even a fuel gauge, as well as a DC to DC converter. And it enables you to very quickly get started on a system level design, which includes all of the blocks that are shown on the architecture. And this is what the board looks like. It's the Max RefDes 179. It's a complete 45-watt 2-cell lithium-ion charging solution for power delivery. So it has the power delivery controller, the fast buck boost charger, the Max 17320 fuel gauge with protection, as well as a switch cap converter, which converts from a 2-cell to a single-cell equivalent voltage to power the rest of your system. So look out for this reference design on our website. So in conclusion, we've seen a lot of solutions offered by Maxim, which really offer the simplest and the most highly integrated solutions for the USB Type-C applications. We have out-of-the-box compliance for USB power delivery, as well as fully integrated solutions which include the charger as well as the Type-C detection, all in a single chip. And that both improves your time to market and minimizes your solution size. So let's take a look at some of the design resources available for all of the products shown today. So make sure to visit Maxim's website at www.maximintegrated.com/USB-C for all of the USB Type-C and power delivery solutions presented today. You can also visit the battery management page at www.maximintegrated.com/battery-management. And you can find all of our evaluation kits as well as the reference design on the website. In addition to that, there's a number of webinar resources, including application notes, design guides, and more. So thanks a lot for listening to this webinar. That's the end of my presentation. And I hope you learned something and enables you to accelerate your designs with these solutions.
Wow, thanks, Sagar, for that informative presentation. That's a lot of material. And I know we're going to get a few questions, but before I open up the Q&A here, I'd like to point out the Contact Us window that's on your screen. If you have questions that go beyond what Sagar has covered today, then you can fill out that form, and we'll be back in touch with you to resolve any questions that you might have. And let's see. Yes, as a matter of fact, we are getting some questions. So Sagar, here we go. Number one, can you share more details about just how the moisture detection feature works in the Max 77958?
Sure. Thanks, Ben. That's a great question. So the way that the moisture detection works is the IC Max 77958 has a built-in analog to digital converter, and it senses the impedance changes on the USB port and compares that with a couple of GPIO pins on the board itself. And when a change in impedance is detected, which is often what happens when moisture is present in the system, the IC is able to, we have a proprietary algorithm which enables us to accurately detect when moisture is present. And when that is detected, it generates either an interrupt or sets a status signal inside the chip, which can be read by the system. And based on that system message, the system can really respond to it as needed, whether it's with an interrupt or maybe shutting down the system or just kind of reducing the power level or voltage level.
Okay, very good. Okay, so second question, and this one is kind of interesting, something I've kind of wondered. How do you know whether or not USB-C or USB with power delivery is needed for an application? And second part of that question is, in what cases should we just consider sticking with standard USB micro B ports?
Yeah, that's another good question. So with USB Type-C or power delivery, we have really the fundamental consideration is the power level. So if the power is less than 15 watts, you're more likely just the standard Type-C is going to be sufficient. Anything greater than 15 watts, power delivery will be required. There may be other considerations. So in some cases, you may have higher voltage on the source, and your system may operate efficiently at that particular voltage. So even though the power may be less than 15 watts, you may still want to use power delivery. The second part of the question for a micro B connector, right? So I understand, people are familiar with it. It's been in use for a long time. But there's really, with the Type-C becoming more and more simple, and with all of these solutions offered which simplify and speed up time to market and reduce the learning curve, there's really not much of a reason to use micro B anymore. First of all, your designs with Type-C will be future-proof. And then second, it also gives you the convenience of the reversible connector, higher power levels, faster charging that the Type-C standard offers. So, the only barrier really was the learning curve and the complexity of Type-C, which is no longer the case with all of these integrated solutions.
Yeah, exactly right. Okay, very good. And here's another one that I've got a lot of USB-C cables lying around, and the question is a special cable necessary for USB power delivery?
Yeah, good question. So there is no special cable required. All of the USB Type-C cables are required to be USB certified. And second, the basic current capability of the cable is 3 amps. So with any system, you're guaranteed, if you have a power delivery system which goes up to 20 volts on the input, you can get 20 times 3 amps, which is up to 60 watts of power. So the standard USB cable will provide that. However, if you want to go higher than 60 watts, up to 100 watts, there are certain cables which have they're called electronically marked cables, which essentially have a power delivery controller built into the cable. So those are rated, that they can be rated up to 5 amps. And so if you do need the power up to 100 watts, then in those cases, you may need custom cables or special cables, but For the majority of the applications up to 60 watts, there is no special cable.
Very good. That's very clear. Okay, you're getting a lot of interest in the 77958, and this questioner says, I understand that the Max 77958 is compliant to PD 3.0, but what can I do if the spec gets updated? So I guess they're trying to future-proof the design.
Yeah, that's a great question again. So, we've dealt with this so many times that you just release a product and then a new spec comes out. And so you're already obsolete from the word go, right? So one of the advantages that the Max 77958 offers is we do have the ability to upgrade the firmware. And I think I mentioned this in the presentation, but there are multiple ways that you can upgrade it. One of the most convenient methods is if you have a microcontroller on the board, which a lot of times, these days, you do have applications which need over-the-air updates for even their system application and so on. So with that same method, the microcontroller or the application processor on the board can program the Max 77958 to an updated firmware. And when and if the standard gets updated, Maxim will release new firmware, which will be available on our website, and you can update that firmware anytime. And more than that, you may also want to add more features on your system itself, even though the USB standard may remain the same. In that case, even the customization script, the method that we talked about to enable all sorts of different behavior on your application, you can also update your customization script in the field, in the same method that I just described. So it has a lot of flexibility and future-proofing for any such scenarios.
Very good. Well, I see by the old clock up in the corner of the screen that we're just flat out of time for questions. I'd like to thank everyone for joining us today and for all these great questions. And also, thanks to Sagar for an engaging presentation. And after we sign off, you're going to see request a meeting invitation pop up on your screen. Now, you can use this if you'd like to schedule a visit with our team. Okay, well, once again, thank you so much for joining us, and we'll see you at the next Maxim Integrated webinar.